how do we add binary numbers? For example, if I give you this 0, 1, 1, 0, and I want to add to it 0, 1, 1, 1. We know the first number is what? 1, 2, 4, 6. Remember the weight. 1, 2, 4, 1, 2, 4, 8, right? So 2 and 4 is what? That's a 6. And this number, 1, 2, 4, 8. 1, 2, that's a 7. What's 6 plus 7? It should be 13. Well, then if the answer is 13, my answer should be what? How do you get 13? 8 and 4, that's 12 plus 1, right? So it should be 1, 1, 0, 1. 1, 2, 4, and 8. What's 8 and 4? 12 plus 1. That's what the answer should be. So how do we add numbers like these? What's the rule for that? Here's how we add them. Yep. 0 plus 0. If you're adding 0 plus 0, the result is what? We'll call this the sum, and this is the carry. What's 0 plus 0? I heard somebody say 2.
No.
0. Is there a carry? No. That's an A. It looks like a U.
Curry.
Yep. Carry 1, but it looks like a U there. That's a U. It looks like an O there. The sum. So what's 0 plus 1 when you add 0 and 1? 1. Is there a carry? No. What's 1 plus 0? 1. Carry is what? And what's 1 plus 1?
0.
That's really a 2. And a 2 in binary is what?
A 1, 1, 0.
0, 1, right? On the left, from right to left, 0, 1, from left to right, 1, 0.
Yeah.
So your sum is going to be 0. You're going to have a carry of 1. Because that's what 1, 1 is actually this one. So when you add them, we apply that logic here. And the other one, let's look at this. What's 0 plus 1? So let's go back here. Let's see if we can get that answer. What's 0 plus 1? According to that one, that's what? That's a 1. What is 1 plus 1? 2. This is a 2. 2 is 0, 1, right? So it's 0, carry 1. What is 1 plus 1 plus 1? 3. Isn't it 3? This is a 3? Isn't that what a 3 is? 1 and 2? So it's a 1 and carry what? This is the carry. 1. What's 1 plus 0 plus 0? Is that the same answer? 1, 1, 0, 1? Let's try another one.
And those
Yes.
consecutive ones, you could have said
That's a 3.
You could have said 1, 1, 0, and then carry 1, and then the 0 and the 1, 1.
Correct. Yep.
Right.
So you add these two, get a 0, carry 1,
The 0 plus
then add the 1 to the 0, makes it a 1, sure.
All right.
Yep. Let's take another one. 1, 1, 0, 1. And 0, 1, 0, 1. What is 1 plus 1? That's a 2, right? 2 is what? 0, carry 1. 1 plus 0, that's what?
1.
1. 1 plus 1.
0 carry 1.
2, that's 0, carry 1. 1 plus 1 is 2, plus 0, that's 2. 0, carry 1. 1 plus nothing will give me what? 1. Let's see if that actually does work. This number, 1101. 1, that's a 13. You're adding to it what? 1 and 4, which is 5. And the result should be what? 18? Do we have an 18?
16 plus 2.
1, 2, 4, 8, 16. What's 16 plus 2? There's 18.
Shouldn't you end up on the same base?
Huh?
Like, isn't that like hexadecimal or something?
This one? I'm giving you this in binary.
Groups of fours.
No, that's just binary addition.
Oh, alright.
Yep. Now, how do we build a computer device that does binary addition? Well, we have something called full adder. It's a one piece. It's a device that looks like this. Full adder. It has two inputs, I'll call them A and B. And it has a carry from the previous state. So we're going to call that carry from previous, I don't know. And it's going to give me the sum here, and it'll carry to the next state. So I'm going to relabel these. This is, we'll call this CN here. And this is the previous one. What should we call it? CN minus 1 or CP? What do you want to call it? CP. So here's your input. This is the sum. And the next state, C next. We're going to list all the possibilities that exist here. And if you want to list all the possibilities, we have three inputs. See them? 1, 2, and 3 on the top. These are my inputs coming in. And these are what? Outputs. How many inputs do you have? 3. Each one has two options, 0 or 1. Think of statistics. Each one has two options, either 0 or 1. You have 3 sets. That's 2 to the power 3. What is 2 to the power 3?
8.
There's only 8 different combinations that can exist. So let me do 8 lines here. 1, 2, 3, 4, 5, 6, 7, 8. And to make life easy on me, I'm going to label them this way. Start with the one on the right, the CP, the most significant, this one, because these are the input, that's the output. This is the most significant on the left. This is the least. I'll go 0, 1, 0, 1, 0, 1, 0, 1. Alternate every digit. The next one, 0, 0, 1, 1, 0, 0, 1, 1. Every 2. And the last one, every what? 4?
Yeah.
0, 0, 0, 0, 1, 1, 1, 1. Look at the numbering, by the way. If you think of octal here, what's 0, 0, 0?
0.
What's 0, 0, 1? 0, 1, 0. 0, 1, 1.
3.
1, 0, 0. 4. 1, 0, 1. 5. 1, 1, 0. 6, 1, 1, 1. 7. So they're in order there. That's why you go 0, 1, 0, 1, 0, 1, 0, 1. If I have another column, if there were 4 of them, we go every what? Every 8. It will be 16 combination. 2 to the 4 is what? 16? You go 16, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 16 times. 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones. 16. 4 zeros, 4 ones, 4 zeros, 4 ones. Then 8 zeros and 8 ones. Let's see what the sum should be. What's 0 plus 0 plus 0? 0. So the sum is 0, and the carry is going to be what? 0. 0, 0, 1. When you add them, isn't that a 1? The sum is 1, the carry is 0. 0, 1, 0. That's still a 1. 1 carry 0. 0, 1, 1. That's a 2. 2. The sum is 0, the carry is 1. 1, 0, 0. What's 1 plus 0 plus 0? Still a 1. 1 carry 0. What's 1 plus 0 plus 1? 2. 0 carry 1. What's 1, 1, 0? That's 2. 0 carry 1. And what's 1 plus 1 plus 1? That's 3. That's 1 carry 1. That's how that device works. We can buy them. They're on the market. So if I want to design a device that will add 4 bits like this one for me, if I want to design a device that will add something like this for me, this is what I'm going to do. I'm going to take 4 of these. 4 of them. Put them next to each other. Except for the first digit, there is no carry. So the carry will be attached to what, the first one?
Ground.
To ground, actually.
Which is
0. Ground is 0, 5 volts is 1. When you go to the lab, you'll see that. So the first one's attached to the ground because there's no carry for the first one. This is going to have 2 of them, A0 and B0. So you're going to have an answer which is what? S0, that's your sum. And you're going to have a carry now, C0. That carry now will go, and it becomes the carry to this state. Because you want to take it to the next digit. And this is B1 and A1. This will be S1 and a carry 1. And that carry will go, and it goes into right here for the next one. And this is 2 inputs, A2 and B2, S2, C2, the carry here, and now I have A3 and B3. And that'll give me S3, and there's the last carry, C3. This is a full adder, each one of these, a 1-bit full adder. So to add 4 bits at a time, that's what the device will look like. If you want to add 8 bits at a time, instead of having 4, how many you'll have connected? 8 of them. And that will add 8 bits at a time. The problem with that, what happens when you have negative numbers? Now we got a problem. how do we deal with negative numbers? So everyone see why the first one is attached to 0 here? Because there's nothing to carry for the first digit. It's really 0. So you attach that to the ground. So your answer is going to be this, 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 and that's the digit. If it's 0, so your final answer when you're adding 4 bits, when you write them in order, will look like this. And that could be 0 or 1, depends on the carry here. So when you're adding 4 bits, that's your sum of any 4 bits that you're adding in that order. Okay, we decide how are we going to handle positive and negative numbers. Now you and I can deal with positive and negative numbers. Well, the way we define them says the human-friendly notation for sign numbers +5 or -3. So we know that's a +5, that's a negative number. Well, how do we know if the number is positive or negative? One of the options we can use sign numbers. In sign number, we look at the first digit on the left. So we can use that and compute to be plus negative. If the first digit on the left is 0, that number is a positive number. If the first digit on the left is 1, that's a negative number. And the rest of them is the magnitude of that number. Everyone see that? 0 for the first bit, that means positive. 1 means negative. So your number actually, the value of your number, will look like this. There is this digit, that's the sign digit or sign bit. If you put a 0 in it, that tells me that number is positive. So what about if I wrote this number in it? This is the sign bit. It's 0, that tells me it's positive. And what's the value of the number? It's the value of these. What is 1, 4, and 8? That's a plus 13 in this case. If I take same size one and I put a 1 here, that's a sign bit. And I put 0, 1, 1, 0. That 1 here tells me that number is what? Negative. And what's the value of that number? Look at the rest of them. What is this equal to? 6? That's actually a negative 6. Now, when you and I go to add numbers, if I said to you, can you subtract or add isn't that the same as what? 5 plus what? Negative 3? And mathematically, what do? We subtract the smaller from the larger. We have to know which one's bigger, which one's smaller. We go 3 from 5, which is what? 2, and what's the sign of the larger? Positive. That's a plus 2. But if I had 3 minus 5, we go, well, that's 3 plus a negative 5. We still subtract the smaller from the larger. 3 from 5, which is what? 2. And take the absolute value. Which number has a larger absolute value, the positive or the negative? The negative, that's a negative 2. Well, when we do it in binary, we do the same thing. Here's in binary. If you want to add, for example, 5 plus 3, which is what? 8. Negative 5 plus negative 3, negative 8, because you're in the same sign. Plus 5 minus 3, we know that's a plus 2. That's a negative 2. That's plus 2, negative 2. It says, in each of the examples above, we must determine which is the larger magnitude. It says it could be the first, could be the second. Then we must subtract the smaller from the larger and finally attach the sign of the larger magnitude. That's how we do them in math. This is an example. If you want to do 5 minus 3 here, it says, although this could all be done, the problem with that, of the hardware, involve you must have an adder, you must have a subtractor, and you must have what? A comparison. If you want to subtract numbers, you want to add numbers, you got to decide which number is bigger. Well, how do we know which one's bigger? That means I need a device that can compare them and see which one is bigger. First thing first. And if the signs are the same, I need to do what? Add them. I need to have a device that will add them. If the signs are different like these, I need to have what? Subtractor. So in my machine, in my computer, I should have an adder, I should have a subtractor, I should have something to compare them. 3 different devices. This is not economical for us. This is a waste of a lot of money. We're going to skip that. If we use sign numbers, we need to have these devices there. We're saying, how about if we try to do them all with just an adder, with one device? You got to play with the math. How do we do that then with just an adder? And the way we're going to do that, we're going to use what we call the 2's complement. Now, before I move forward, let me show you how you find the 2's complement of any number, which is straightforward. Then I'll come back to it. Find the 2's complement of, pick any number, 1, 0, 1, 1, 0, 1. I have the toes instead of 2. The 2's complement of 1, 0, 1, 1, 0, 1. The first step is you find the 1's complement. And the 1's complement is you change all the 1's to 0's, all the 0's to 1's. So the 1's complement of that number will be what? 0, 1, 0, 0, 1, 0. Change all the 1's to 0's, all the 0's to 1. After you finish with that, add 1 to the answer. Always. So what's 0 and 1? 1, 1, 0, 0, 1, 0. And that is the 2's complement. So the 2's complement of 1, 0, 1, 1, 0, 1 is that value. We do the 1's complement first. We change all the 1's to 0's, all the 0's to 1's. Then we add 1 to the answer. Let's take another example. Find the 2's complement 1 0 1 0 0 1 1 0 1 or 0 0. I'll leave it. I'll end it at 1 here. How's that? To add, well, I could add zeros. I mean, it's not a big deal. There we go. 0. Let's leave the zeros. Who cares how big the number? Because it looks like leading zeros, but I need the weight of them, location of it. So let's say that's the number. So first you got to find what? Find the ones complement. Which is what? What do we do? We flip all the zeros to ones, all the ones to zeros. That'd be 1 1. I'm going from right to left. 1 1 0 0 1 1 0 1 0. Next we do what? Add 1 to it. What's 1 and 1? 2. 0 carry 1. What's 1 and 1? 2. 0 carry 1. What's 1 and 0? 1 0 1 1 0 1 0. And that is a 2's complement. So the 2's complement of that number is 0 1 0 1 1 0 1 0 0. Another way, there's another mathematical way of doing it, by the way, but it's more complicated. That's the quick way to do it. I'll show you that answer in a minute. How do you find the 2's complement? So the book said instead of having an adder, comparator, and subtractor, 3 devices, we're going to try to eliminate 2 of them. Just use 1 device, that's an adder, to do all the stuff I need to do. And it says, signed binary numbers are normally or nearly always stored in 2's complement. The leading bit is still the sign bit. 0 means the number is positive. So if the leading bit is 0, you store it just the way it is. If that bit is not a 0, if it's a 1, we take the 2's complement of that, or we save it in 2's complement. The negative number is stored as the binary equivalent of 2 to the n minus a in the n-bit system. For example, negative 3 is stored as the binary for 16 minus 3, which is 13. And by the way, if you look at negative 3, if you write the 3 negative, remember, negative 3, I'm going to show you what that number is. Since that's a negative number, so the first digit is 1, and what is the digit value for 3? 0, 1, 1. So to store that, we don't like to use signed numbers, we use the 2's complement. So to find the 2's complement, what is the 1's complement of that number? 0, 0, 1, 0. And we add the 1 to it, which is 1, 0, 1. Now, if I'm using 4 bits for that, actually, because we're dealing with 4 bits here, this would be 1, 1, 0, 0, the signed bit here, right? So if I'm using 4 bits for that, just in case the number is big, and I use 1 for that, 1 to indicate that's a negative number, that's the sign, and 0, 0, 1, 1. So the 1's complement And if you add 1 to it, what are you going to have? 0 and 1, that's 1, 0, 1, 1. And what's the equivalent of that number in decimal?
13.
Because there's a 0, I don't need the 0 here. That's 13. That's how the negative 3 is stored, as 13. Why? Why 13?
Opposite and plus 10. isn't it?
Well, how many digits I'm using? 4? What's 2 to the 4? What's 16 minus the 3?
13.
That's the 2's complement. That's how mathematically we do them. You can do that number that way, but we just do them easier this way. We carry 4 bits for the number and 1 sign bit. So anytime you have a negative number, that sign bit is 1. We do the 1's complement. We add 1 to it, so we save the negative 3 as 13. If I have a negative 7, that's negative. This is the sign bit. What is 7 in binary? 0, 1, 1, 1. Right? Take the 1's complement of that. The 1's complement of that is what? 0, 0, 0, 1, 0. Add 1 to the answer. What do we have? 1, 0, 0, 1. I don't need that 0. It's leading 0. 1, 2, 4, 8. What's 1 and 8? 9. What is 2 to the 4? Minus 7. What is 2 to the 4? 16 minus 7? 9. That's how we store that negative 7 as the 2's complement, which happens to be a 9. So, and you'll see the advantage in a minute. I don't have to use adder, subtractor, comparer. Only one device, the adder. So we take all the negative numbers, we store them in their 2's complement.
So when it looks at it though, it still has to determine if it's negative or,
Oh no, you'll see what we're going to modify that design just a hair,
yeah.
and we just add them. Now, the problem with that is when you're adding numbers now, let's say I want to add 5 to negative 7 or 9 to negative 7. I'm adding actually 9 to 9, which is what? 18. And if I'm using 4 digits, that's outside my range. I have an overflow.
You don't though because the overflow is what it should be.
The overflow is what?
It was what it should be.
No, because it's going to be a 1 here, which is a negative number,
Oh, yeah.
right? So now, what happens here? It says, in either way to find the storage format for a negative number in 2's complement, use the following step. Find the 1's equivalent of the magnitude, complement each bit, 0 to 1, 1 to 0, add 1. That's what we did. That's how we find the 2's complement. So again, you look at the 1 is 0, 0, 0, 1, that's the plus 1. You know. If you want to get a negative value, for example, what's negative 8? Well, negative 8 happens to be as plus 8. Why? Because when you look at negative 8, that's 1, 1, 0, 0, 0. 1 means negative, the sign, and that's the 8. Now do the 1's complement. Add 1 to it. 1 and 1, 0 carry 1. 1 and 1, 0 carry 1. 1 and 1, 0 carry 1. 1 and 0, 1, and there's the 0. And what's that number? 8. 16 minus the 8 is 8. So it's the negative 8 is really stored as positive 8 in 2's complement. So there's a chart here. For example, the negative 1 is stored as what? What's 16 minus 1? 15, doing the complement. If it's a negative 4, what's 16 minus 4? 12, stored as 12. So all negative numbers are stored as the complement of a number. That's what that chart is telling you. So how do we add them then? It says, first, the reason we like the complement, here we go. The reason the 2's complement is so popular in the simplicity of the addition, to add any two numbers, no matter what the sign of each is, we just do binary addition on their representation. I don't have to look and see which one is bigger. I don't have to see if that's addition or subtraction. We add them. If the number is a negative number, we find the 2's complement, we add the 2's complement, add the 7 to it, and there's my answer. If both numbers are positive, leave them alone and add them. If both numbers are negative, you find the 2's complement, both of them, and add them. It's always addition. This is whenever we add two positive numbers, each beginning with the 0, because sometimes you're adding, for example, plus 8 and plus 9. What's plus 8 plus 9? That'll have a 1 for carry, right? That's going to make that number look like an odd number, a negative number, because you exceed the size. The size is 16 for 4 bits. And we get a result that looks negative because of the carry. Begins with the 1. We have an overflow. You exceed the size of that. The same thing if you're adding two negative numbers. If you take a -4, a -4, and a -6, a -4 will be stored as what? 12, right? A -6 will be stored as 10. What's 12 and 10? 22. That's more than 15. So we have an overflow there too. So anytime you're adding two negative numbers or two positive numbers, there's a chance of an overflow. And you know that because it looks like your number is coming out as an opposite sign. You're adding two negative, you're getting a positive. You're adding two positive, you're getting a negative. And there are some examples for that. So what do we do then with that? The sign number, the carry out of the high order bit, is ignored. An overflow occurs if the addition process operates on two numbers of the same sign to produce a result of opposite sign. When you have two positive number and your answer looks like negative, that doesn't make any sense. You ignore that overflow. If you're adding two negative numbers, how do you know negative? The last bit is 1 and your answer is positive, you ignore the overflow because you have an overflow there. So that says, anytime it says, when we're adding sign numbers, the carry out of the higher order bit is ignored. So let's see how we're going to do that. A few examples here. Let's say I want to add +5 and +4. That's straightforward. That's +9. Do you think +9, do you have an overflow or not? No, so I'm good. What's +5? When you write +5, isn't that 4 and 1? And what's +4? Just 4. When you add them, 1 and 0, 1, 0 and 0, 0, 1 and 1, 0 carry 1, 1 and 1. 1 and 0, 1, and there's no overflow for the last one. So my answer is 8 and 1, which is 9. There is no overflow here coming out of the higher order bit. Now let me change that just a little bit. Now if you're looking at this, you're going, wait a minute. Well, that looks like an odd number. That looks like an odd. These are even. 0 means positive, odd means negative, right? Well, if you do the 2's complement of that number, what happens if you do the 2's complement of this? What is the 2's complement? Isn't the 1's complement 0, 1, 1, 0? And add 1 to it. That gives me what? 7, right? So you know that's not true. There is no overflow coming out, so I shouldn't really be doing complements here. But if you see an overflow, we're going to do a complement. So my overflow, there was nothing here. I didn't have any overflow. I don't have to do anything to my answer. There's my answer, 9. Now, let's see ones where you're going to have an overflow or negative values here. Oh, this is dead now. So let me take one that gives me some negative values. Let's say I want to add negative 5 plus a negative 4. What's the answer? Negative 9. But here's the problem. Negative 5 will be stored as what? 2's complement. What's 16 minus 5? 11. 8 and 0, 1, 1. 8, 2, and 1. That's 11. Negative 4. What's the 2's complement? Negative 4. What's 16 minus 4? 12. Now let's add them. Those are the numbers. 1 and 0 is what? 1. 1 and 0? 1. 0 and 1? 1. 1 and 1? 0, carry 1. Uh-oh. In the carry, which is the last bit, there's a 1. First, the value we're going to ignore, but that tells me my number is negative. And if it's negative, how do you find the positive value of that? You do the 2's complement to convert it to a positive. Let's do the 2's complement of this number. What is the 2's complement of that? 0, 0, 0, 1, add 1 to it, and what's the result? 1, 0, 0, 1. And we know because that's a 1, that tells me that's a negative number. So it's negative what? Negative 9. That number says, oh, you got a negative number, and if negative, then you do the complement of that. The value of this is a 9, and the minus tell me that's a negative 9. Now, if the numbers are positive and negative, let's see what the result is. Let's say plus 7 minus 5. What's the result? Isn't that a plus 2? So the 7 will be what? I'm almost done. 0, 1, 1, 1. That's a negative number. I've got to find the 2's complement of it. What's 16 minus 5? 11. That's 1, 0, 1, 1. Let's add them. 1 and 1. 0 carry 1. 1 and 1. 1. 1 carry 1. 1 and 1. 0 carry 1. 1 and 1. 0 carry 1. Wait a minute. Let's look right here. You adding 1 and 1 here. What's your answer? 0. Two negative numbers, positive. Not just the carry, there's a couple of things you're going to deal with. You're adding 2 negative numbers here, and your answer is positive. That can't be. Now, you're adding a positive to a negative. Your answer could be positive. The book says ignore the carry, so I don't have to do a complement here, because these signs are opposite in sign. It will never be a carry. Now, if I reverse that, let's see what happens. Negative 7, 2's complement. What is 16 minus 7? 9. Is that 1, 0, 0, 1? And the 5 is what? 1 and 4? One and 1? What's 1 and 1? 0, carry 1. 1 and 0 is 1. 0 and 1 is 1. 1 and 0 is 1. Notice this digit. That's a 1. That says, oh, the number might be negative. What's the complement of that? the complement of this, that's a negative number. Let's see what the complement. So that's 1, 0, 0, 0. Add 1 to it. What do we have? And that's a negative 2. So how does the machine do all that stuff for us? How does the machine know to check this, not to check that, to see if it's odd, even? How do we fix that problem? Here's what the design looks like. Might have a picture of it here.
You said the last of those 4 bits, you have to check that and see if it could be negative. You have to check the sign or not.
Yep, if this is a 1, that's a negative number. So you can take the complement of that to get the answer. Do we have a picture here in this book that shows you what that device looks like, the adder? It will be coming up later in the course. Let me just see if I can quickly spot it. Where the machine does all this work with just an adder, not an adder and subtractor and comparator. Where'd you go? Where'd you go? It's like third chapter 3 or 4 in the book. I know it's late. So lots of steps to look for. It's not just straightforward, oh, some, odd, even. Somewhere in the course, I can't find the book quickly, and show you, actually we add 2 exclusive OR to the 4 of them, the 4-bit adder, and that will make it do subtraction, addition, everything. I just don't see it quickly. I'll look for it next time and I'll show you what that picture looks like. There is in the back of the book somewhere toward chapter 3, 4. We've shown you what that device, we can do addition, subtraction, comparison, everything with one device, and that's the adder. For homework assignment, let's get you, let me kill the camera.